So yesterday, okay, we were talking about both Hooke's law and energy in simple harmonic motion. Okay, so just as a quick review here, Hooke's law tells us the restoring force in a spring is equal to negative k times x. Okay, that is that it can it is related to both how stiff the spring is, the spring constant k, and how far the spring is displaced from its unstrained length. All right. So with that in mind, I want you to give example 7.4 here a try. Just write it down real quick, because so if I hang this spring from the ceiling, what force is pulling on it? Gravity. All right. Since the object's not accelerating, in fact, it's just hanging there, the net force is 0. So the force of gravity is being offset by the force of the, what's keeping it from falling? The spring. Okay. So what we have to say is Hooke's law, the force in the spring, or the restoring force, is equal to, in this case, the force of gravity. All right. So we can say that we have negative k times x equals m times g. Right? Because they would add up to 0. All right, so when we do this calculation here, okay, we have the mass, so we know what m is. We have to convert it to kilograms, okay, and we know that the spring stretches 0.5 meters. So we're looking for the spring constant. So I'm just going to move the negative x over to this side. Can k ever be a negative number? K is an absolute value. If you ever get a negative number for it, it's just because you forgot to move a negative or forgot to put a negative in, but k is always a positive number. Okay, just use whatever value you get, absolute. Okay, so I'm just going to divide both sides by negative x here. Okay, and then I will have k equals 0.510 times 9.81. Okay, divided by, let's say, negative. Well, actually, this will be negative times negative because this is down and the force is up, right? Okay, so we'll have, like we said, it doesn't matter because k is always a positive number anyway. So we'll go divided by 0.5, right? And that'll give us our spring constant. That's weird. Unlock all buttons. No? Weird. All right, so 0.510 times 9.81 divided by 0.5. All right, so we're looking at that it's going to have a spring constant of 10. What's the units for spring constant? Newtons per meter. Okay, we had newtons on the top here. We divided by meters, newtons per meter. Okay. Essentially, it's how many newtons would you have to exert in order to stretch the spring by 1 meter, newtons per meter. All right, so that's our Hooke's law stuff. Is that ringing a bell for everybody? Okay. Almost always when we deal with Hooke's law, you're going to have an object that's not oscillating, and that's how you can tell it's a Hooke's law question. If it's a law of conservation of energy question, the object has to be moving with simple harmonic motion. Okay? For Hooke's law question, it doesn't have to be. It can be, but it doesn't have to be. So most of the time with Hooke's law, it'll just be a spring is stretched this much, and there's no oscillation involved. Okay? All right, we are going to skip that because we don't have to do that kind anymore. All right. And we're going to skip because we don't have to do that kind anymore either. All right, let's look at question number 1 here together first, okay? So number 1, I have a mass that's oscillating on a horizontal frictionless surface, and it's attached to a spring whose spring constant is known, okay? What is the mass's displacement when its instantaneous acceleration is 4.11 meters per second squared left? All right, so I know the acceleration is 4.11 meters per second squared, okay? And that's left. And then we have K. K is 8.21 newtons per meter, and we know that the mass is 0.724. All right, so we have to envision this. This object is on a horizontal surface, and it's going back and forth, back and forth. So gravity is not a factor now. All right, what's the only force causing the spring to do what it's doing? Yeah, well, just the spring itself, right? The restoring force in the spring is the only force in this system. Since it is the only force in this system, it is then by default the net force. Okay, just thinking back to unit 2 here. Since it's the only force, it's the net force. So can I say that the force in the spring equals F net and then transfer to this? Is it okay for me to say that if it's the net force? All right, now can I solve for the instantaneous, the displacement, when its acceleration is 4.11? Right, so now all I have to do is solve for x. So I just divide by k. Actually, I'm going to take negative k over there, so I'm solving for positive x. Okay, and then plug in my numbers. So 0.724 times 4.11, and that'll be left. Okay, divided by k, which is 8.21. All right, so when we do that, we should get 0.362 meters to the right. I'll just double check that that's what we actually get. Oh, not divided, times. Okay, 0.362 meters. Connor. I took it off because I was solving for x. All I did in my head was if the acceleration is left, the displacement is going to be opposite that. So I just haven't wrote it on here yet, right? But my displacement is going to be to the right. It has to be opposite. Okay, and they have right here as well. Okay. All right, I want you guys to try 2 and 3. They work very similar to that one. I'll make them a little bigger so you can read them. Some terminology here. Okay, terminology, amplitude. Okay, amplitude means the maximum displacement from equilibrium, right? So if I have, if I'm looking at kind of that spring, so here's where the spring is attached, okay? This would be, okay, so if equilibrium is right here, okay, out here would be the maximum displacement to this side, okay? And then whatever it is here, okay, this would be the maximum displacement to this side. So that would be the amplitude of the motion. How far does it go? All right, everybody follow me on that? Essentially, how big is the movement? That's why, like for sound waves, for example, if you want to make sound waves louder, you have to do what to them? Amplify them, right? You use an amplifier, okay? An amplifier makes the waves bigger, makes the displacement of the waves larger, right? So that they have more volume, okay? And then obviously this here would be our equilibrium position, right? So remember that out here and here, we would have only what kinds of energy? Potential, and here it would be all kinetic. Okay. Give number 2 a try. See how you do. All right, so question number 2 is asking us essentially to compare 2 positions in the oscillation of this mass. Okay, this position here, where we only have potential energy at the maximum amplitude, and here, where we have only kinetic energy and are thus moving as fast as possible. All right, the equilibrium position is always where the speed is greatest, but the acceleration and force are 0. Out here, the speed is 0 and the acceleration and force are greatest because that is where the spring is either stretched or compressed at its maximum amount. Okay, everybody follow me on that? All right, so since they tell us the maximum amplitude, we know, okay, that we have 1/2 kx squared, all potential energy, equaling, since we're looking for the maximum speed, 1/2 mv squared. Those two have to be equal because they're talking about the same motion, okay, at a point where it's either all kinetic or all potential, right? If it was placed halfway in between, then we would have some potential and some kinetic, just like a roller coaster, okay? So we're looking for the maximum speed, so I'm just going to divide both sides by 1/2 of m. The halves will cancel, and then I'll square root to get v. All right, so V is going to equal then the square root of 4 times 1.12 squared divided by 0.05 kilograms. Okay, so all right, so we're looking at about 10 meters per second. Yeah. All right, so it's a conservation of energy question. If you see the word maximum amplitude, that is a point where there is only potential energy. If it talks about maximum speed, then we are talking about the equilibrium position and we only have kinetic energy. All right, if it's talking about anywhere in between, okay, then you're going to have a little bit of 1/2 kx squared and a little bit of 1/2 mv squared. Okay. All right. Try number 3. Very similar, okay? Very similar to what we just did in number 2. All right, so this one's a little bit different, but I mean, it's still going to have the same general principles. All right, we're looking for the period of oscillation of this mass spring system that has an amplitude of 12.25 centimeters and a maximum speed of 5.13. Okay, the spring constant is 5.03. All right, so the formula we have for period of a mass on a spring is 2 pi times the square root of m over k. I have k, but I don't have m. Right? But they do tell me the maximum speed and the maximum amplitude, which means I could do a law of conservation of energy type situation, which might allow me to calculate what I don't have, which is mass, right? We just did a question. The last question you did was calculating the mass using the law of conservation of energy. So this is the same thing with an extra step on the end. All right, so I would have 1/2 kx squared, the maximum amplitude in this case, okay, equals 1/2 mv squared. And I would just bring the half of v squared over to this side. The halves will cancel, and that will solve for m. And then I can plug m into this formula. Okay, so we would have 5.03 times 0.1225 squared. And guys, this happens all the time in these kind of questions. They really like to throw things in centimeters and just see if they can catch you. Okay, using the wrong number. Obviously, it has to be in meters because we're dealing with energy here. All right, and then we're dividing that by v squared, which was 5.13. Okay, and that'll give us the mass. So 5.03 times 0.1225 squared divided by 5.13 squared. All right, so it's not very heavy. It's about 29 grams or so, something like that. So now we're going to plug that into our period formula. So we'll go 2 times pi times the square root of our answer divided by the spring constant, which was 5.03. All right, so the period of this motion should be about 0.47 seconds. All right, so it takes a little less than half a second for it to make one complete oscillation. Okay, and remember that for this thing, one complete oscillation means starts here at equilibrium, goes out to here, goes past equilibrium to here, and back to equilibrium. That's one full cycle for a mass on a spring. Okay, it's out, all the way back, and back to equilibrium again. It's got to hit both maximum amplitudes and essentially go through equilibrium twice. All right, questions on how that one worked? Okay, now probably that little bit there might have thrown you the first time you read that question on, okay, how do I get period when I'm given all this energy information? Okay, try question number 1. Makes you do a little bit of everything. A little bit of Hooke's law, a little bit of conservation of energy, okay? A little bit of the period formula for a mass on a spring, right? Just kind of some of all of it there. Okay, so for number 1, okay, we've got a 2.50 kilogram mass, and it's on a horizontal spring, so gravity's not a factor here, okay? And it has an amplitude of 0.8 meters. We know the spring constant, so we know what K is. We're trying to find the acceleration of the mass when it is at a displacement of 0.3 meters. Okay, so what am I going to use to solve part A? If I'm looking for acceleration, the only way I can find that is through the use of forces, which would involve the use of whose law? Hooke's law. Yeah, part A is going to be a Hooke's law question. All right, I'm going to have negative kx equaling the net force. Right? It's a horizontal spring. That's the only force that's involved. So I can calculate the acceleration. I know the displacement, and they told me the spring constant, so I can find what A is, and I also know the mass. Right? So it'll just be negative k times x over m, and that'll give us A. All right. So its displacement is 0.3. They didn't say what direction, so I can't really give a direction for the acceleration either. In this case, I can calculate the magnitude of the acceleration, but I can't give a direction here because they never told me what the acceleration was. Right? I mean, we could say maybe back towards equilibrium. That would be about the best we could do for a vector. Okay. All right, so we're going to have 40, okay, negative 40 times 0.3, okay, and then we're going to divide that by 2.5. Right? So that'll give us our acceleration. All right, so our acceleration will be 4.8 meters per second squared towards equilibrium. It's about the best we can do. Okay, questions on how we solve part A. So basically, anytime you're asked to solve for acceleration, the only way to do that is through Hooke's law and the use of net force and sum of all forces. Okay. Now, for part B, if I want to calculate the maximum speed, that's probably going to involve the use of what? Conservation of energy, because it's part of kinetic energy, right? It's going to have the most kinetic energy at equilibrium, so that's where it'll be moving the fastest. They also tell me the maximum amplitude here in the top part of the question. So I can go back to 1/2 kx squared equals 1/2 mv squared and solve for v. So divide both sides by half of m. The halves will cancel, square root, and that'll give me v. So we'll have 40 times 0.8 squared divided by 2.5 kilograms, square rooted. All right, so it'll be its maximum speed will be 3.2 meters per second. All right, and then the period. Well, I have everything I need to use the period formula for a mass on a spring at this point. All right, T equals 2 pi times the square root of m over k. In fact, I could have done that at the very beginning too. That was all stuff that was given to me in the question, just a matter of plugging in my numbers here. Okay, everybody good with that one? All right. On a unit exam, I probably wouldn't ask all three of those things in one question. Okay, I would probably have separate questions for each one of those concepts. One's Hooke's law, one's period of a simple harmonic oscillator, and the other is a law of conservation of energy question. So you'd probably be looking at 3 separate questions on the unit exam for that. All right, we're feeling a little more comfortable with this conservation of energy stuff. Okay, Hooke's law stuff. All right. Okay, I want you guys to just do number 2. Do number 2 and we'll call it a day.